Welcome back to the 21st quarter of complex numbers. In this 21st quarter of complex numbers, we shall learn Laurent series. Herein, we are going to deal with the review of Taylor series that we have learned in one of our earlier lectures. Then we shall define Laurent series, we shall deal with the coefficients of Laurent series, and we shall deal with some examples. Let us recall the Taylor series. Let us suppose that f is a function and this function is prevailing in the set U, which is part of complex plane, and this function we propose to be analytic. So here everything rolls around the definition of analytic function. Now here we shall be trying to understand this in a better way. In the entire complex plane, we consider a region where the set U is present. Here you may consider some holes here and there which are voids in the set U, and we are not bothered by that. Now we consider some function in the region of a disk of radius r centered around z0. Let us suppose that this is a point z0, and around this point we consider a circle of radius r. And this circle or disk of radius r is entirely contained into U. Then the function f has a power series representation, and that power series can be expressed by f of z equal to summation ak into z minus z0 to the power k, where k rolls from 0 to infinity. The most fascinating part of the Taylor series is that this very coefficients ak, they can be found by obtaining kth derivative. The coefficient ak can be obtained by finding kth derivative of the function at the point z0 divided by k factorial, and you have to ensure that this k is greater than or equal to 0. Less than 0 will mean integration, which is not a part in this definition. This is a very useful thing because it analytically helps us to find the function at the center point at the inside the disk around the point z0. So under the title of Taylor series, we have tried to represent logarithmic function, exponential function, sinusoidal function, and so on. But the question is that if the function is not differentiable, so here we need derivative, and if the function is not differentiable at some point, for example, then what happens? Let us deal with such an example. F of z is equal to z upon z square plus 4. Now, if you consider z to be equal to plus minus 2i, then the function, the fraction in the denominator will be 0 and the function f of z will blow. So this is not differentiable at z equal to plus minus 2i. We can say that undefined there. So if we consider the complex plane and if we consider 2 points 2i and minus 2i. Then we can consider a circle of radius r around a point, say z0, and we can deal with the issue of Taylor series or power series. But if we are considering that at these two locations, then the Taylor series is insufficient to handle the problem. Similarly, for logarithmic function, we have the negative real axis discontinuity because the logarithmic function is not continuous on the negative real axis. So it's not differentiable on negative real axis. And for such situation, if you try to build a circle of radius r around this, so this is the region where the problem prevails. This is the place where it is not differentiable. How to handle such situations? Laurent series offers us help at such locations. Now let us deal with the Laurent series. We are considering the similar situation that we have considered for power series or Taylor series, and there we consider a set U. Moreover, this set U is a part of complex plane, and the function which is prevailing in the set U is analytic, and it is analytic in some region starting from a disk of radius r up to disk of radius uppercase R, and both the boundaries and the included area is included into the set U. Then F has a Laurent series, and the Laurent series can be expressed in the similar way, the way we have expressed the Taylor series, except the fact that your series is a doubly infinity series, not starting with 0, rather starting with minus infinity to plus infinity, same power series, same Taylor series, ak into z minus z0 to the power k. And this series, when k is equal to 0, it will be a0. When k is equal to 1, it will be a1 into z minus z0 to the power 1. And so on. We can have a forward motion from this point and backward motion from this point. A suffix minus 1 into z minus z0 to the power minus 1. So I'm writing in the denominator, and so on. We can go on expanding. That converges at a point. Before that, I would like to state that this is the set U, which is part of the complex plane, and we have a function that is analytic. For example, this is some region where there is a void. This is not the part of U. And then we consider a circle here again. Here, this is the point which is Z0. And we consider a circle of radius small r and a circle of radius capital R. So here, let me state this as small r and the another one as capital R. Now this void is not included, so Z0 is not included into the set U, but the disk that we are considering between two circles small r and capital R is fairly included into the set U. This series converges at a point of annulus and converges absolutely and uniformly in such a subannulus which are redefined here that R is less than S. So S you have to consider greater. So I'm redrawing that. S you have to consider greater than small r. So here we are talking about the outer boundary of this, and then T is less than capital R. So we are talking about the between area. Sorry, so here it should be between two. So here we are talking about the included area. Annulus means when we consider the negative real axis, we have a function discontinuity. And if you consider disk in this situation, so you can start from here and you have to terminate below the negative real axis. So the annulus is not complete. That is the meaning. Now let us consider the function f of z is equal to 1 upon z minus 1 into z minus 2. So obviously the point z equal to 1 and z equal to 2 are the spoilers. When we substitute z equal to 1 in the denominator, we can obtain 0, which leads to undefined range of the function, and similar thing happens for z equal to 2. In which of the following annular regions is the function differentiable? That is a question. So here we have different regions which are defined by mod of z lying between 1 and 2 and so on and so forth. So here for all these regions which are defined mathematically, you have to consider and you have to understand whether this z equal to 1 and z equal to 2 is included in that region or not. That is a question. Let us consider these regions one by one, and the first region under consideration is mod of z, as I said, is lying between 1 and 2. 1 is not included and 2 is not included. So obviously it is the region lying between 1 and 2 excluding 1 and 2. So here you can see the shaded region which is centered around origin of the coordinate system, and we are considering the region in between 1 and 2. I mean to say that a disk of radius greater than 1 and a disk of radius less than 2, where 1 and 2 is not included. In such a situation, it does not contain the singularity at 1 and 2 in the given annular region. Therefore, this function is analytic inside the given region. Now let us deal with the second case where we are talking about the region which is mod of z minus 1 lying between 0 and 1. So mod of z minus 1 means we have to locate a circle or a disk which is centered around 1, and here you can make the mark, and we have to consider the region which is lying between 0 to 1 excluding 0 and excluding 1. So this means that we are considering the radius of the disk between 0 and 1. So 1 will make it up to 2, and here the annular region is centered at 1 and does not contain singularity at 1 and 2. Therefore, the function is analytic inside it. So this is to be marked analytic inside the annular. For the same function, let us consider the region of interest where mod of z minus 1, that is a circle centered at 1. So here you can see this is 1 and this is 1. A circle centered at 1 having radius that lies between 0 to 2, excluding 0 and excluding 2. So here you can see the radius greater than 0 and less than 2. So in this situation what happens? 1 is not included. Therefore, this will not become 0. But 2 is included. So that will spoil the game. So here this 2 will spoil the game. And therefore, it has a singularity which is at 1 that is not included, but the singularity at 2 is included, so that the function f is not analytic inside the region which is shaded in this diagram. So final conclusion is that this is not differentiable. Now this is another interesting problem where we are considering the same function f of z, which is equal to 1 upon z minus 1 into z minus 2. And in this region, we have to check whether the annular region, in the annular region, function is differentiable or not. And now here we consider mod of z minus 2. It means that we are talking about a circle which is centered at z equal to 2. So this is the point for which the x coordinate is 2, real coordinate is 2. So we have to consider a circle, or yes, of course, a circle which is centered around z equal to 2 and it lies over the entire spectrum 0 to infinity. 0 is not included here. So I want to make a point here that 0 is not included, 0 is excluded, and this region goes up to infinity. So here this way you can go to infinity and this way you can go to infinity. Now under this consideration, z equal to 2 is excluded, but z equal to 1 is included. So the annular region is centered at 2, does not contain the singularity at 2, but it does contain the singularity at 1. So the function is not analytic inside. So the conclusion is that it is not differentiable. Now in the last quarter of this example, we are considering that mod of z is lying between 2 to infinity. 2 is not included. That is very important thing here. 2 is not included. And we have to consider a circle of radius just above 2 up to infinity. So here the shaded region can be extended up to infinity, does not matter. And this is extended to infinity, this is also extended to infinity. So 1 is not included because mod of z is greater than 2, and 2 is also not included, and therefore both the singularities are excluded from the annular region defined here. Therefore, the function is analytic inside, and as it is analytic, we can conclude that this is differentiable. So as I remember, we can conclude that this is a differentiable zone, this is also differentiable zone, and the last one was differentiable zone. And here this is not and this is not differentiable. So here the coefficients ak, which are uniquely determined by the function f, but the question is, how do we find them? Let's roll through a problem that we have started with. F of z is equal to 1 upon z minus 1 into z minus 2. This function is analytic in the entire complex plane except the point 1, 2, because when z is equal to 1, the denominator becomes 0 and the function f of z blows. Similar thing happens at z equal to 2. Now, we are interested in finding the Laurent series in the annulus, which is a circle of radius 1 and circle of radius 2 lying in between these two circles. Now, let us suppose that this is a complex plane, and when z is equal to 1, we have a circle of radius 1 I'll draw later on, and when z is equal to 2, then again we have a circle of radius 2. So here I'm interested in a circle of radius 1. Similarly, I'm interested in circle of radius 2. So as suggested, annulus is mod of z lying between 1 and 2. We are looking forward to the region which is lying between these two circles. Here we are going to use a wonderful trick, and the trick is that we are going to rewrite this 1 in a smart way. Denominator is same, z minus 1 into z minus 2. Now here we have written z minus 1 minus z minus minus plus 2. So this z is eliminated and minus 1 plus 2, this becomes 1. So this 1 we have written in a smart way as z minus 1 minus z minus 2. Now the first term is like this: z minus 1 upon z minus 1 into z minus 2. So we can eliminate this z minus 1 and we can straightly write it is 1 upon z minus 2. The second interesting term, this minus sign is retained here, and the second term is z minus 2 divided by z minus 1 into z minus 2. So here we have liberty to eliminate z minus 2 upon z minus 2, and we are left with minus 1 upon z minus 1. Now we have learned that q to the power m, we are talking about this series where m we roll from 0 to infinity. So this infinite series can be written as 1 upon 1 minus q. This we have done earlier. Now I want to fit this term and this term into this representation. This representation is valid as long as the mod of q possess value less than 1. That is the restriction. Now we have to smartly adjust again this representation. So for making that adjustment, we shall take 2 common, we shall factor 2 and we shall factor minus 1 also. So minus 1 by 2, inside bracket we have 1 minus z by 2 for the first term. I hope you gather this. Minus, here we need to factor only z, so that we have 1 upon z into 1 minus 1 by z. So for this particular term, 1 upon 1 minus z by 2, we can write summation that rolls from 0 to infinity z by 2 to the power k, provided this entity z by 2 mod of that is less than 1. Minus 1 by 2 is retained. Here minus 1 upon z is retained, and this term 1 upon 1 minus 1 by z we can write as summation k rolling from 0 to infinity 1 upon z to the power k. Now here again we intend to make some smart adjustments. So this minus 1 is brought into the summation sign with no r. Then z to the power k is prevailing here in the same fashion, no issue. Then this 2 and this 2 to the power k. So that will be 2 to the power k plus 1. So the first term we have made a suitable adjustment. Then this minus sign is brought inside. So this minus is brought inside. So here it becomes plus. Then here we have z to the power k, and here we have z, where k rolls from 0 to infinity. So here we have in fact 1 upon z to the power k plus 1, where k rolls from 0 to infinity. Sorry, this is 0 to infinity. Now we shall rearrange this and we shall replace k plus 1 by new k, and k equal to 0 will be k equal to 1. So I mean to say that we are changing the notation to m, which represents k plus 1. And if you like to rewrite it in terms of k, then our summation is rolling from 1 to infinity. The earlier one was rolling from 0 to infinity. So here we have k rolling from 0 to infinity minus 1 z to the k upon 2 to the power k plus 1 plus k rolling from minus infinity to minus 1 into z to the k. So here the z to the k we have brought into the numerator by adjusting the limits. So here we continue with the same function f of z is equal to 1 upon 1, z minus 1 into z minus 2, and we have written the series for this function as two components in the range 1 to 2 for mod of z. Now if we choose mod of z between 2 to infinity, in one of the earlier slides we have seen that both the singularities, that singularity at 1 and singularity at 2, they are out of the annulus, and therefore the function is analytic and hence differentiable in that region. Now we are going to explore the series expansion for this. Now let us work out the coefficients. Now when k is equal to 0, I'm talking about a0, and for a0 I'm writing 2 to the power 0 plus 1, that is 2. So minus 1 upon 2 is the coefficient for the first coefficient of the series. Then a1 we shall try. So here this k is to be replaced by 1. So minus 1 upon 2 to the power 2, that will be 4. Sorry, minus 1 upon 4 will be the next coefficient. Similarly, a2 will be, you can see, minus 1 upon 2 to the power 2 plus 1, that is 2 to the power 3, that is 8. Similarly, you can work out the negative coefficient of the first component, a minus 1. So here k is replaced by minus 1, so 2 to the 0 will be 1. So minus 1 will be the first coefficient in negative part. So a minus 2 will also be minus 1 upon 2 to the power minus 2 plus 1 will be minus 2. So here 2 to the power minus 2, sorry, 2 to the power minus 1. So this will be minus 2, and so on and so forth. You can go on working out that. Now here we are again going to the trick of rewriting the geometric series, and for that purpose we have written this 1 upon z minus 1 into z minus 2. This we can factor very nicely in the way we have done it earlier, as 1 upon z minus 2 minus 1 upon z minus 1. This we have done. Now that here we are going to use this annulus demarcation very appropriately, in the sense that we want 2 upon mod of z, and this is less than 1. So that will lead us to the definition of perfect geometric series. And if we divide on both sides, we have 2 upon mod of z, I should write 1 upon, I'll rewrite 1 upon mod of z. This is less than 1 by 2. Less than 1 by 2, I can write less than 1. That is fairly okay, no problem. So this makes a perfect geometric series approximation. So here from this term we can factor z common, and it will be 1 minus 2 over z, minus, here we factor z again, so z into 1 minus 1 over z. So here this restriction fairly takes us into the zone of discussion where this can be nicely written as perfect geometric series. So for these two parts, in the next step we are going to write geometric series. So 1 upon z is common, so this z is appearing here and this z is appearing here. Now this is nicely written in terms of a geometric series where k rolls from 0 to infinity, 2 upon z to the power k and 1 upon z to the power k. So in this step we are interested in taking this 1 over z inside the summation, and again this 1 over z we want to take inside the summation without spoiling the meaning. So here I'm writing 2 to the power k in the numerator, and in the denominator I'll have z to the power k and z. So z to the power k plus 1. So this will be my new term. Now here I have to roll summation where k rolls from 0 to infinity. Now that I do not want this k plus 1 term, I want z to the power k. So here I can rewrite the summation where k rolls from 1 to infinity, and here we have z to the power k and one term back to this 2 to the power k. So it is a 1 power less, so it is 2 to the power k minus 1. Similar thing we can rearrange here. So 1 over z to the power k is inside summation, and if I bring this z in the denominator inside the summation, it will be z to the power k plus 1, and this summation will roll from 0 to infinity. And as I do not want k plus 1, I want k only, so I can roll summation from k equal to 1 to infinity. And in the next step, I do not want the negative powers of z. Therefore, I'm rewriting my summation where k rolls from minus infinity to minus 1. And here we have z to the power k. So instead of writing z to the power k, which is in fact z to the power minus k, I'm preferring to write z to the power k and rolling my summation from minus infinity to minus 1. That is allowed. So in this problem where we are considering the function f as 1 upon z minus 1 into z minus 2. So this product we are considering, and this function blows at z equal to 1 and z equal to 2, obviously. So here we have Laurent series expansion for the region. We have mod of z lying between 1 and 2, strictly mod of z not equal to 1 permitted, and z equal to 2 is not permitted. In the second annulus, where z is lying between 2 to infinity, mod of z is lying between 2 to infinity, it's not Laurent series. Sorry, it is a Laurent series in this region. And now we shall look forward how the coefficients roll in this. Now let us suppose that we are talking about a0, and when k is equal to 0, we are left with 2 to the power minus 1. So 1 by 2 minus 1. So this will turn out to be minus 1 by 2. Similarly, if you try working out a1, you will arrive at minus 1 by 4. Then a2 will be minus 1 by 8, and so on and so forth. Now let us talk about the negative coefficients. A minus 1, this will be minus 1. A minus 2, if you plug in, I mean to say k equal to minus 2, this value, then the coefficient will be minus 1, and so on. Now again, what if we choose another annulus which is mod of z minus 1 lying between 0 to 1. 0 is not included and 1 is not included again. So this will form an analytic function. It will be differentiable, and the Laurent series for this will exist. Now 1 upon z minus 2 we can rewrite as 1 upon z minus 1 minus 1. No harm in doing that. So here we are just flipping the sign. We are taking minus 1 common, and we dare to flip the first term to the last and last term to the first. So 1 minus z minus 1. So this makes a perfect geometric series where minus is taken common and z minus 1 to the power k, where z minus 1 mod lies between 0 and 1. Now the function f of z, which is 1 upon z minus 1 minus 1 upon z minus 2. So here we are writing minus summation k rolling from 0 to infinity z minus 1 to the power k. So here we are using this much part for this one. So we are replacing this here, and the remaining portion remains as it is. Now when we combine that and we change the powers of z so that k rolls, instead of from k equal to 0 we are starting at k equal to minus 1. We have done earlier also this kind of adjustments. So minus 1 into z minus 1 to the power k, where mod of z minus 1 rolls between 0 and 1. And here I would like to pass a remark that if you try to find out a case and you make a list of a case, you will be able to conclude that these a case, all a k's are equal to 1, sorry, minus 1 for k rolling from minus 1 to infinity, and all a k's will vanish. That is, it will be 0 for all k's less than minus 1. Now let us deal with another example where the function is sine of z upon z to the power 4, and we already know that it is an analytic function except at the origin of the coordinate system, that is complex plane. So here we are going to have a complex plane, and in this complex plane we can talk about the function except at origin. And we are now interested in knowing in this annulus what is the Laurent series centered at origin. Here we recall the sine z series, and we have already done this. Sine of z is equal to minus 1 to the power k into z to the power 2k plus 1 divided by 2k plus 1 factorial. Now if you roll k from 0 to infinity, you will be able to write the infinite series, which is in fact flipping with signs in the alternate terms, and only the odd powers of z are prevailing. And when you work out this series, it will be z minus z cube upon 3 factorial plus z to the power 5 upon 5 factorial minus z to the power 7 upon 7 factorial, and so on. Now we are interested in sine of z upon z to the power 4. So here we have to employ multiplication 1 upon z to the power 4 to this series, and the new series that we obtain is as appearing on your screen. Now here you can work out the coefficients. A minus 3 is equal to 1, a minus 2 is equal to 0, a minus 1 is equal to minus 1 upon 3 factorial, then a0 is equal to 0, A1 is equal to 1 upon 5 factorial, A2 is disappearing 0, A3 is equal to minus 1 upon 7 factorial. So at this point, we recall the Taylor series expansion of the function f of z is equal to summation ak into z minus z0 to the power k, where k rolls from 0 to infinity, and mod of z minus z0 is less than r. So here you have to find a point z0, and you have to consider a disk of radius r centered around z0. Now, AK can be calculated according to the Taylor series expansion as kth derivative of the function at z0 upon k factorial. Now, how about the Lorentz series in such situation? F of z is equal to ak into z minus z0 to the power k, where k rolls from minus infinity to plus infinity. So here z minus z0 has to have value between small r and capital R. So if this is the z0 point, then we are talking about the region between a disk of radius little r to a disk of radius capital R, and we are talking about the annulus between these two disks. So here we are considering this region. Now, function may not be defined at z0, like our function was not defined at origin. We need a new approach back to the Taylor series, and here we are going to use the Cauchy's integral formula. So ak, which is kth derivative of the function at z0, and the function may not be defined at z0, divided by k factorial, it is equal to 1 upon 2 pi I integral, or a disk of radius s which is less than r, less than this capital R, f of z upon z minus z0 to the power k plus 1 dc. So here s is between 0 and capital R. So one can show the similar facts for the Laurent series. So here goes a theorem. If f is an analytic function in the region of disk of radius small r to capital R centered around z0, then f of z can be expressed by ak into z minus z0 to the power k, where k is rolling from minus infinity to plus infinity, and the coefficients using the Cauchy-Riemann theorem rather, can be expressed like this. For any s, we are considering a disk of radius s which is greater than r and smaller than capital R for all k in the complex plane. Note that it is not useful. This does not seem at all useful for finding actual values of k, but it's useful to estimate AKs. I appreciate your patience for leading up to this point.